Hello folks, so this is your 2020 February March session, paper 4.2, and the question number is 8. This question is concerned with the chapter magnetic field. Magnetic field. So the first question says, explain what is meant by a magnetic field. So it is a region or area around a magnet, let us say magnet, in which another small magnet or certain magnetic pole or certain moving charge particle or maybe a current carrying conductor feel a certain type of force. See, there are four things we have to consider. It is either a magnet or a magnetic pole, any pole of the magnet, or a moving charge particle, or a current carrying conductor. So if they experience a force, the region where they experience a force is the magnetic field. But it is the first two are compulsory, and the second, third and fourth one, they are not compulsory, because at certain angles they might not feel force, but most of the in all of the other angles they feel that force. Number B, the apparatus shown in figure 8.1 is used in an experiment to find the magnetic flux density B between the poles of a horseshoe magnet. So horseshoe magnet, modified one. So these are the poles. This thing and this thing are the poles. So actually this thing is the pole, this is, and the other face here which is hidden is the poles. Assume that the magnetic field is uniform between the poles of the magnet and zero elsewhere. So it is a direct assumption, though it's not always true. It has been assumed that a rigid the rigid metal rod of length 300 millimeter is fixed in a position perpendicular to the direction of the magnetic field. So the field lines will be acting like this. The field lines will be acting somewhat like this, either this direction or reverse, and this rod is perpendicular to these things. So the rod here is perpendicular to this thing, means that theta angle is equal to 90 degrees. So we are just given blatantly this thing. Yeah, the poles of the magnet are both 45 millimeter long, so that means along this 45 millimeter this conductor feels a magnetic field, and other portions do not feel the field. There's a current in the rod that causes a force on the rod. Yes, when there is current, when the angle is 90 degrees, when there's magnetic field, definitely it should feel a force, and F equal to BIL. Theta is 90 here. The balance is used to measure the measure of force. So it is the pan of the balance, pan balance actually. The variation with current I of the force F on the rod is shown in figure 8.2. So as current increases or decreases, the variation in the force is as shown in the graph in the next page. So this is the graph. See, this is the graph. So in this graph we can say when current was I was 0, force was 0. As current increased, the force also increased proportionally. We can see straight line through the origin, so it is proportional. Calculate the magnetic flux density B. So the formula is simply F is equal to BI and L. BIL. So if I take any point here, so I think the best point would be this one itself, because it will be 9. If it is force, it is 9 millinewton, and if it is current, it is 5 ampere. In others we have to go to decimal, but here not decimal. So I can have F is equal to 9.0 millinewton, so it is into 10 to the power minus 3, equal B is to be found. I is 5 ampere into 5.0, and length is equal to this 45 millimeter. It is not 300 millimeter because the magnetic field applies only in this portion. So 45 millimeter, and that will be equal to in terms of meters it is 0.045. So therefore B is equal to 9.0 into 10 to the power minus 3 whole divided, it is a 5.0 into 0.045. So by calculation it will give us 9 exponent 9 divided 5 equal to divided 0.045. Sorry, I made a mess out of this. 9 exponent minus 3 divided 5 equal to divided 0.045. So it is 0.04. So if I write in 2SF, it is 0.040 Tesla. So 0.040 Tesla. Now the next question, sorry. Yes, in a different experiment, so it is different from what we have been doing here. Experiment, electrons are accelerated through a potential difference and then enter a region of magnetic field. So they have been accelerated here, then they enter a region of magnetic field. The magnetic field is onto the plane of the paper, so it is into means we have this crosses here. Magnetic field is into the plane of the paper, that means away from the observer, which we are. And is a perpendicular to the direction of travel of the electrons. So electrons like this and magnetic field like this, so definitely this perpendicular. Explain why the electrons follow a circular path when inside the region of the magnetic field. So why circular path? And the first reason for this is when a charged particle enters a magnetic field perpendicularly with angle 90 degrees, the first thing is that they are traveling at 90 degrees. The first reason is, number one reason is that electrons travel at 90 degrees angle to the direction of B, Had it been not 90 degree, the path would have been helical. So at 9 degrees, they just keep on repeating that path, and so that's why it forms an arc of a circle. If strong enough and if it can complete one full circle inside the field, it might repeat that. If not, it will make a circular arc, then exit. The first thing is that they are at 90 degree angles. The second is that because of this, the second reason is that because of this, the force and the velocity, they are always perpendicular to each other. The force creates this Lorentz force, which we call as the Lorentz force, is always perpendicular to the direction of velocity of the electrons. So inside that field, the force applied by the Lorentz force, what we call as, is always perpendicular to the direction of velocity of the electrons. And since it provides the centripetal force, and it is FL, which generates, let us say, generates the centripetal force. So that's why it follows a circular path. And the next could be that the logic that we can apply is the speed of the electrons inside the field doesn't change. So it can happen only on circular path. So the third one is no change of speed inside the field. It can happen only in circular path. On other paths it is not possible. So with these evidences, we can say that the path is a circle, and the region also is somewhat like this. Now number 3, state the measurements needed in order to determine the charge to mass ratio. So the formula for charge to mass is ME is equal to V square by BR by BR. Now B we do measure by using flux meter or Hall probe. R we can measure and we do measure, but V we don't measure. So that's why V will be equal to, it can be obtained from the value of the accelerating PD. So what we have is this V is equal to root of twice EV by M. This V is the accelerating PD, electronic charge, and yes, so that's why initially when it was accelerated, so we can easily measure this V. So this V gives this V, and with this we can obtain this. So the measurements that we should have is accelerating PD, which causes the acceleration of the electrons. Number 2 is magnetic flux density, and number 3 is the radius taken up by the electrons, path of electrons. So these are the measurements that we need to find the value of E by M. So this is the total answer to the question.